So I decided to give this whole devlog thing a go. Um, right now I'm in a bit of a planning session more than development, but I'm at a crossroads when it comes to simulation software. I'm trying to figure out exactly what domain to pursue. At first, I came into it looking at pretty much all of them, and I've realized why you have to spend like 30 years just to be a master of one domain, even just fluids. Um, and really, like, I have an interest in all of it. I love all engineering, and I love that simulation software is a lot closer to engineering than web dev, which is what I did for over a decade. Um, but I think the engineering I'm most interested in is this sort of futuristic um, augmentations to the human body or complete control over genetics or the software of the body, like morphogenesis. Um, and the thing is, I don't really have deep domain knowledge in biology to PhD level knowledge to go out and do those things directly. So being able to access them from software is really interesting to me. And so from doing a little bit of fluids and atmospheric dispersion modeling, I really enjoyed it, but I see that its applications aren't really directly applicable to biology, other than things like blood flow or air in the lungs, maybe. But pretty much all biology problems are multiple physics systems working together. Um, but anyway, I'm gonna do some research here and mess around with my simulator. I'm sharing this more as an insight into who I am and what I'm trying to build, um, and a way for people that don't know me that maybe I reach out to trust me more as a legit software engineer. So one thing that would probably be cool is to show my current simulator. Um, I've built this entity component system for a real-time interactive simulator. Let me see. This is app. So this is the main loop here. Like in a game, uh, these are the systems that only run once, and these are the systems that run on each frame. And I've built a wrapper around FluidX 3D, which is this OpenCL, I think Lattice Boltzmann CFD solver that's really fast, um, so that I can include it in my simulator. Right now, I've got this default scene. I think it's a F117. I've got a little mirrored cube map just so that you can see the edges better. And this white rectangular box is the fluid domain. And as you can see, you can kind of fly around dynamically. When we're running this simulation, you can also do this, which is kind of what I was going for. I wanted to make a real-time simulator. And I was kind of picturing biology when I was doing it. I was thinking, if you wanted to design a stent for a heart, you could scan in the full mesh of the heart with the plaque and fly around it like this, put the stent in, design the geometry, mesh, and run a simulator. I've since then learned that that might be harder than I thought, but I still kind of want to try it because I think it would be a really cool human in the loop way of doing this. Because I've noticed a lot of simulation software, you get these 1D outputs or 2D outputs, or the thing runs for 10 minutes and you get a couple of frames that you can put in pair view and look at. And I don't know, I just don't, as a software engineer, I don't like how it's broken into so many complex steps. it's cool to have it all unified in one place. And I have no idea if there is a business use case for this sort of thing, but I'm pursuing it nonetheless. So let me show, you can see all of the entities. So the F-117, and these are the components on each entity. And you can dynamically get rid of these things and bring them back. It's pretty cool. This is a solver configuration, so I can edit these things. Fluid physics, viscosity, stream velocity, etc. I can bring these up or down. I am going to, oh yeah, I've got these cool little gizmos for moving things around. I do need to make it easier to select the domain versus the jet. I haven't thought about that yet. That's right, backspace. Okay. Go back to this. All right, let's tell you what I'll do. Let's run it so I can show it off. Oh, I've got particles and ray marching volume fields at the same time. It's kind of weird. Let me choose one of those. Ooh, there is a little lag. Turn one off. There we go. Get the particles. Pretty cool. Alright, go back to volume. And it's not doing anything now. Let's see if we redo the simulation, what happens. Oh, cool. The other thing I've learned from messing around with these simulations is the vast majority of the effort goes into making sure that they're accurate. And there's a lot of really heavy math behind that, which is one of the reasons that you need PhD level talent to actually build these things. So I did want to build my own solver, and I've done a finite difference method solver in WebGL, which taught me a lot. I'm a lot better at PDEs. Some old math knowledge from college coming back. But honestly, so much goes into those solvers. I think it's better maybe to integrate into existing solvers that I know work and show clearly the parameters and outputs. So I'm thinking about building these tools where it's very easy to mesh, load geometry, do your meshes, pick your solver, maybe even coupled solvers together, which I've got to learn more about. Do the runs, see them live, fly around them like this. Some won't run that fast. In fact, many will not run real time, but maybe I'll still have the ability to fly around and it just won't be synchronized in real time. And then perform optimizations, the whole loop. Do the whole loop in one place, see the logs. That way they can verify the math. But that's what I'm thinking. What I want to learn is more on the biology side now. And a few things I have learned is that the really low level biology, like molecular dynamics, is so complex that even like, I don't know if it was milliseconds or nanoseconds, it's like takes a really powerful GPU to run for a very, very long time. So real time is completely out of reach for that. It is interesting though, because if you could run it faster, what could you do? What could you optimize? What kind of, could you like invent some kind of nanotech for the body or come up with the perfect drug for every scenario? It's cool, but given the limited compute power that's needed for that, I think I like the idea of going for more of continuum scale biomedical simulations, because like with aircraft, we're just doing fluid dynamics. You're solving Navier-Stokes. So if you can solve the same level of equations for the body, it should be just as fast, or almost as fast, because the systems are a little more coupled. So I'm thinking that is what I want to pursue, but pursue it as a scientific software engineer, and building these building these systems and products around it to make it easier for the scientists and engineers to solve problems and do their work. Anyway, these little, oh, that actually rotates the domain. That's not good. I should probably lock that down, because it's definitely supposed to be centered. Okay, that's something to change. I was trying to rotate the jet. Cool. So I got ChatGPT to give me a pretty big readout of just all of the different fields of simulation engineering, just to kind of review these things and wrap my head around the ecosystem better. It seems like on the aerospace and defense side, the ecosystem is very mature with tools like ANSYS and COMSOL multiphysics. I don't think I can compete with those people at all. I mean, probably your best in for working with that kind of software is to master the tools themselves, using them, which really positions you more as a mechanical or electrical engineer, or whatever the system is you're working on, which isn't really my interest. I like generic software more. If I were to do a domain, it probably would be some sort of maybe tissue engineering and biology. So this, I think I have a pretty firm grasp on. You have the geometry, which I can't remember all of the formats, but STL is one of the good ones. I think there's like VTK, OBJ, which doesn't have as much information, and you have vertices and indices. You can have a volume mesh, which, so there's some parallels with game dev, where in game dev you mostly just have surface meshes. I'm not sure if volume meshes are ever a thing, but with real simulations, what's inside three-dimensionally matters as well. So it's kind of interesting, even building the simulator. There's a lot of linear algebra to convert. Oh, Jesus Christ! What am I? Ah, there's a lot of linear algebra behind converting surface meshes to volume meshes when you can do it. A lot of assumptions you have to make, and when you're rendering an OpenGL, you don't really render a surface mesh as well. So there's a lot of back and forth conversions that's pretty interesting, because OpenGL wants vertices and indices. So that, I can tell that that's a pretty big problem, but it's been solved by a lot of this software. It's just that if you're making new software, you have to keep that in mind. Materials, I guess I need to do a little bit more. Probably won't need to. Materials as it relates to simulation software. I'm assuming that's what it's made of, different physics constants. Density, yield strength, so that's what structural, thermal expansion, conductivity, right? So I guess it depends on what kind of simulation you're doing. the material would have all kinds of different constants and maybe differences across the entire mesh. Okay. Boundary conditions. This is like your inlets and outlets. Kind of where the simulation begins and ends. The mesh itself, in a lot of these I've used voxelize the mesh into 3D, and each voxel can have a flag representing if there's a solid there or a boundary, but it gets really complex, especially different meshing techniques, which I definitely don't have a firm grasp on now, but you rarely ever uniformly mesh things. That's what's interesting to me. Areas where there's more computation, you would have more cells, and there's all kinds of algorithms for creating these meshes, or engineers may do them or edit them by hand. The governing equations, these are ODEs, PDEs, that's all of these down here. I don't know how good I am in explaining this, but ODE is just a function based on time, but not based on space. It's the same everywhere. Rigid bodies, apparently circuits. I kind of want to look at these things. Mechanics would be what I'm familiar with somewhat. PDEs are based on space and time, like Navier-Stokes, heat. And Navier-Stokes is the only one that I've really have a firm grasp on. But PDEs are very interesting. I really do like the math behind all of this, but I think mastering it to the level of a professional numerical modeler just takes so much time that I don't have. Discretization, this is how you represent these equations and geometry, all of it, in a finite space. So lots of ways to do this, lots of methods like finite difference, finite volume, finite element, spectral. There's a bunch of them. It's kind of how you integrate those equations, create a fixed finite domain, and solve the equations. It's always an approximation, and there's a way to calculate the error of the approximation to know how accurately you're following the physics. And from my current knowledge, finite volume is one of the best, but it's very difficult. It's very rigorous math, and finite difference is pretty easy, but it's not very accurate at all, and it's also kind of slow. I think spectral is used a lot for like hypersonics. Lattice Boltzmann, yep, GPU friendly. I was just about to say that. Because it's a grid, so it's really easy to represent on a GPU, since GPUs just solve the same like linear algebra multiplications and stuff many times at once. SPH, I remember this, yeah, okay. It's where you represent particles in the grid, or a mixture of, it's like putting particles on the faces or something like that. I can't remember exactly, but you can represent water with this pretty nicely. And also it's just like, it's almost like an animation technique for showing the calculations that you're getting. And that's another thing I've learned, is that the shaders, like, so you have these vector fields of velocity and scalar fields of pressure when it comes to fluid dynamics, and they're usually big arrays, and the way that you visually represent them, where they're meaningful to the eye, can vary dramatically. There's lots of different shader techniques, just like the particles I just showed, or the volume ray marching technique. There's a lot. There's streamlines. You can do slices, whole bunch of stuff. So there's almost a whole field of knowledge right there that you could master. I find that stuff really fascinating. I mean, the solver is just where the numerical math happens. Usually its own process, and it's doing all of the heavy lifting. It's doing discretizing these equations. Post processing, I guess, would be the visualization, looking at the results, processing them. Validation, this is probably where I'm the weakest because you have to have very deep mathematical knowledge, but based on all of the parameters and how many cells you used and so on, you can calculate the accuracy. And then I guess also this could be comparing your results to real world cases, like a real world wind tunnel, things like that, or in biology, like experimental validation, that kind of thing. Parameter estimation, I'm not sure what that references. We'll come back to that. The other one that's really interesting to me is optimization and inverse design. This is actually what kind of caught my interest because I saw some sort of topology optimization for, I think it was a car frame, and the AI just ran, I don't know if it was genetic algorithms or some other optimization technique that ran until it designed, kind of like the perfect car frame, and it looked almost alien-like, but it somewhat matched the skeleton of a flying squirrel. So it's like evolutionary pressure built the flying squirrel skeleton, and then there's an algorithm that can actually build that same skeleton. So that was fascinating to me because I imagine the future possibilities of something like that. In a way, just editing topology is cool for like missiles, aerodynamics, jets, car bodies, things like that, frames. I'm sure there's a lot of other use cases, but it made me think more about inverse design. Like maybe, especially with biology, you want the perfect drug, or you want some ability to manipulate the body in a way that's never been done. And you have that as a goal, and then you could use algorithms to start from the goal and create it, like blasting all these different ideas and genetic algorithms. Now, from all of my research, that's completely far-fetched. Most optimization, you have to have a very clearly defined problem and what's called a fitness function, and then it can gradually improve it. Radical improvements, no one's really figured out a way to do that. But I think it just feels like there is an intuitive way you could maybe mix generative AI with some of these optimization algorithms, and maybe build some kind of software that can invent radically new things that humans can't even think of. And that's probably the most exciting thing to me about the world of simulation. Surrogate reduced order models. I know a little about this. It's basically you run real simulations a whole bunch of times and you train an AI model, or it's like with physics informed neural nets. You have like Navier-Stokes or some physical equation as the I can't remember what it's called. It's like the function for training it. I can't remember the name. It's been a while since I messed with AI. But yeah, once that's trained, then within a range of difference, it can approximate the outputs very fast. So I don't know. I've heard mixed things. I don't know if it's that awesome or not. I know I've heard it's good for digital twins when you just need quick approximations, but I'm not really sure. Deployment, I mean, this is just deploying the software on different platforms, I guess. I'm not sure. Live data synchronization, this would be digital twins. And this is another area I think is very interesting. You're keeping a software version of some expensive hardware that is updated live sensor data, sometimes linked where you can actually make actuators perform from the software. And so you could do like predicted maintenance. What else was it? Just generally seeing information about the status, like maybe you're checking a boiler and you want to know all of the details. You can literally click on it in the software. And then one of the probably more cooler is like you can simulate scenarios that might happen. Like, what if this gets too hot or this happens? Will this overload? So there's a lot of really cool stuff there. Decision and control loop. I don't know. That's kind of generic. I don't know. That feels like what I just described with digital twins. Okay, so let's go down. The thing about these mathematical foundations is I know I could learn all of this, but it takes so much time. I hate having to constantly build and, find a way to make money. I wish I had infinite time to just sit down and crack open a math book and just learn all of this. So it is all really interesting. This is all probably my favorite use case of math. I've never heard of DAEs, constrained multi-body systems. What does DAE stand for? Do math. Differential algebraic system of equations. Okay. Derivatives are not present for all variables. A stuck implicit system. Huh. I don't really intuitively understand what that is. I'd have to spend some time on it. That's interesting. So, multi-body systems. Okay. Circuits have that. Plant models. Yeah, see, something I really need to move into. Conservation laws, so, like basics of physics. You're conserving mass, conserving momentum, etc. I think that's pretty much everywhere, and it parallels in all of these systems. Variational formulations, weak form, energy minimization, virtual word. I don't remember. These words sound familiar, but I do not remember anything about this. I don't think I'm going to dig into it right now. Stress and strain, viscosity, hyperelasticity, poroelasticity, viscoelasticity. Okay. Models. Dimensional analysis, scale laws. Similarity. Alright. That's BEM. I've never heard of that either. Acoustics and electromagnetism. BEM. What does that stand for? Boundary element methods. Maybe I have heard of that. Converting continuous boundary integral equations to a system. These discretization methods take a while to learn. Like each one's like 50 hours of learning to really have a strong grasp. I feel like the only one I really have right now is finite difference. Okay, let's move on. Yeah, I know I need to review linear algebra quite a bit. It's, wiggling these matrices into certain states that you can solve. I would like to build intuition on that. Okay, so we got the domains. I think with my simulator, I'm going to try to hook up several of these open source tools. I got FluidX3D already. I think OpenFOAM is the most used open source CFD tool, and I think you can do a whole bunch of stuff in it, other physics and coupling and stuff. So that one should be interesting. I don't know if this one's open source. I think it's paid. That's another thing I might pursue, is just make this thing open source. I do want to get work, get some active contracts, make some money, help people solve some problems, but I think making this open source might be cool, because there doesn't seem to be a very strong visual simulation software that's free. Solid structures mechanics. Yeah. Need to learn this. I know a lot of this stuff, finite element analysis is common, and they're looking at how much a material is going to bend, or stretch, fracture, all these things. I saw this in school a bit. Thermal stress. Electromagnetics are really interesting to me. Yeah, not much to say there. I've seen some of these simulations that actually show like the magnetic fields. You have like a electric generator or antennas or whatever. Bioelectric fields will be really interesting to see. Cool. Multibody. Yeah, this is really interesting to me because honestly, I think about what I'm really into, which you would almost call transhumanism, but not the creepy surveillance state transhumanism, like more of extropianism, upgrade the human body. Um, and Neuralink is pretty cool, brain computer interfaces like that. But I think where it's going to get really interesting is where you have some kind of nanotech, because the body is nanotech. So you need nanotech to completely integrate with the body. But currently, we don't have that, and it's extremely far fetched. So, robotics and controls, that's the real augmentations right now. A prosthetic limb, any bionic organ that could be done, um, any of that stuff. And then also, it's really interesting. Robotics are interesting to me from a like automation standpoint, especially having these humanoid robots that could do repetitive work that humans may not want to do. Free up time and stuff. So I don't know. I'm very interested in that as well, and I think a lot of these things are very important. Control theory is a beast too. I've dabbled, but man, I did not realize like you could make a career out of control theory. There is so much to it. I've seen what they're doing with these reinforcement learning environments. NVIDIA's got some really cool software like MuJoCo and Isaac Sim doing some pretty cool stuff there. Oh, yeah. Yep. Heard about this one. I want to check this out. Apparently, this is a really powerful multi-body solver, so I'll probably integrate that. And I heard Modelica is really good for coupling as well. I went to the website and didn't really see a whole lot, though. This is kind of confusing. The domain I actually care about the most. Yeah, I mean, how electricity like sodium potassium channels influences heart rhythmic pulsing or something. Blood flow, very interesting. Tissue mechanics. See, and I'm very into strength training and just imagining what the body might be capable of. So this is all very interesting. So one thing that frustrates me about biology is it's focused so much on trying to fix problems that there's no room for trying to upgrade the body further. Because I almost think if you approached it from upgrading the body, you'd be able to go backwards and fix other things. But I don't know. Reaction to fusion, that's like, morphogens. That's part of morphogenesis, which is how things grow and shape in the body. Reaction and diffusion. I know like reaction diffusion simulations deal with like how things disperse. Need to learn more cell signaling fields, growth remodeling, agent based. So I know agent based models are when you have individual agents that all have some governing equations to how they work. Multi-scale. See, the multi-scale coupling, kind of fascinating to me as well. It mirrors meshing to me in that in certain regions you might simulate something at a much lower level, and in other regions where you don't care as much, you may just approximate or simulate a higher level system. I gotta check out SimVascular. I think FEBio is a open source solver for the heart. Nonlinear finite element analysis in biomechanics and biophysics. Large deformation problems in biomechanics and biophysics. Cool. Yeah, I'll have to play with this. Shafts, open phone console. See, I'd love to play with COMSOL and ANSYS some, but man, I mean, they don't. You can't even use it as a hobbyist for free. It's like hundreds of bucks a year just to be a hobbyist. It's nuts to me how they do that. I guess I could watch tutorials. Meshing and pre-processing. Yeah, so this is why I don't fully meshing. There's so much to it. So triangle meshes are what I've the most familiar with. Tetrahedral is apparently one of the more accurate ways of representing these cells. Voxel grids are, think like Minecraft, cubes on a grid. Point clouds, you have points in 3D space, and the distance between them is what constructs the mesh. Um, Solid geometry, and the rest of these I'm not really sure. Implicit surfaces. I don't know. Meshing, adaptive refinement. I've worked with a solver that does that, where it figures out how to refine the how many cells are in a certain location. It shrinks the mesh down. Remeshing for different mesh morphing. So much to all this stuff. Model setup. Yep. Coordinate systems and units. That's aggravating. Parameter sweeps. Casual. Okay. Yeah. Well, yeah. I mean, that's solver integration. You build an API or library around it, whatever. Okay. Data formats. That's covering a little bit of everything. Which GPU APIs or HPC APIs, if that's what you want to call it, to use. All of that, blah, 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 blah. Slurm for scheduling on GPUs. Yep. Software patterns. See, the software and GPU stuff is, it's pretty easy to pick up, I think, unless you get into the really, really deep stuff. Like some of the deep optimizations that you can make. You could definitely make an entire career field out of that. Software patterns, I've gotten a lot better at these over time, but now with vibe coding, it's so crazy what you can do. You can just ask it, like, what's the best pattern, and then it tells you, and as long as you know a little bit about software, you're like, oh, that's like the decision I made seeing Graphs versus ECS. ECS to me is a lot more scalable and kind of like a plug-in system. And I had AI tell me that. I'd never worked with a ECS. Then you can get help creating the registry and everything else. This is one reason I'm trying to move away from pure software into an actual domain with a lot of knowledge, because I at least see in the near future that a decent, like a mid-level software engineer can vibe code the world just about. So it's a problem. Yeah, this was all the different visualization techniques I was talking about. I don't know what lick is. Line integral convolution. Cool. Looks kind of like a terrain map. That's a cool one. The current stack. ParaView is open source and you can visualize all sorts of things in it, but that has got to be the most unintuitive software I've ever used. Like it is all over the place. You have to click in like 50 different places just to load one mesh. They really over-engineered that. But Vulkan's something I'm trying to learn. A lot lower level GL. I don't know if you'd call it a language or API. OpenGL's been pretty easy to learn, but Vulkan and WebGPU are kind of similar. WebGPU being the web version, but they're both incredibly low level. Three.js is, like an engine above OpenGL. I don't know. I don't see the point in those. I kind of like having my own OpenGL engine because it, takes a day to make this little framework that I can use and make all of the optimizations I want to make for the project I'm working on. But Three.js is really easy. Put the model here. That's it. Put it in this coordinate space. Done. ImGUI and Qt are both desktop UI UX tools. ImGUI is really simple. That's what I was using in my simulator to configure settings. Qt is huge. This massive suite for doing any kind of desktop interface you could imagine. Very, very heavy. A lot to it. Precision remote rendering. Yeah. This is a pretty good review. I feel like, other than the deep math, I've got a better understanding. I've been learning this stuff for I don't know, 6 months maybe on the side. And, I have had an active contract with an atmospheric dispersion model for 4.5 years. But I only recently really had to learn the math and physics when we started going deeper. I've been able to just work on software, Linux administration, the web apps, desktop apps. I only had to know what was coming out of the solver. I did have to change a few things in the GIS system and WinField viewers, but none of it was that hard until recently. So, okay, verification to the solve the equations. Yeah, so this is all of the different ways to validate, verification versus validation. There's a difference. Yeah, okay, let's see. Validation, are these the right equations? Did we solve them correct? Okay, so verification would be more that's interesting. It's very hard to explain the differences between these two because you could use the entirely wrong equations, and that would be whether it's valid. And the verifications is you use the right equations. Did we actually solve them correctly? Yeah, I could imagine this gets incredibly complicated from a mathematical standpoint. This is where all these applied math PhDs are focused. I'm sure this is probably the vast majority of the work. Cube hypersampling. Monte Carlo. The only thing I've done with Monte Carlo, I know it's like you do random tests over and over and over and over and over until you cover an entire domain. Like you could solve pi by drawing a circle in a domain and then dropping infinity dots randomly and count the ones outside the circle and the ones inside, and that ratio can give you pi. I'm sure there are way more complex versions of Monte Carlo though. Cube. Bayesian uncertainty. Worst case analysis. Optimization. I wouldn't mind, optimization strikes me as something to get into quicker because I learned, I think, the basics of this with gradient descent for learning how neural nets function because that was fascinating to me. But it's basically applying that to topology optimization or optimizing parameters and so on. And I think inverse design definitely is born out of optimization. I would love to sit down with a textbook one day or a few months even, take off work and just go into these. I've used this one before. I don't know exactly how it works, but I researched how the equations work and implemented it sort of, and did the thing where you have a projectile Angry Birds style game and it optimizes the shape of the projectile. It's really dumb 2D simulation. Did that a couple years ago. Genetic algorithms I've messed with it. They converge so slowly. That's the only thing. It almost feels the same as just randomly trying things, but I don't know. So many of these though. Surrogate assisted would be you have one of those surrogate models that's running very quickly, so you're able to try a bunch of things very fast to approximate where the optimizations might be. Wow, a lot more to this than I thought. Okay, inverse design. Let's see how it separates that. Oh, okay, so how you build your fitness functions. Is it going to be parameters on boundaries, source terms? A source term, I learned this with atmospheric dispersion modeling, is the amount of something. In the atmospheric dispersion, it's the amount released, like the mass released. So I don't know how that applies to every domain, but interesting. Yep, topology optimization, valves, heat sinks, implants, microfluidics. Oh, topology and shape are two different things. Wow, topology is material and shape is geometry. Interesting. Didn't know that. I was using that term loosely. Porous scaffolds, metamaterials, compliant mechanism, heat exchangers, materials. Field and control, pacemaker, drug dosing schedules, robot control, thermal control. Yeah, you can use this for control algorithms, and I know that's how they optimize, like if you've ever seen Boston Dynamics robots dancing around doing backflips and stuff. Some of that is first human programmed mimicry, but you can use reinforcement learning and optimization to dial it in. It's perfect. Joint optimization. Wow. Yeah, so this is definitely, I mean, I don't recognize the majority of these things. I have a lot to learn. Autoencoders. I learned this one time, like VAEs. I don't remember. I think maybe like compression is like compresses information down. Reinforcement learning is kind of like an AI training itself in an environment. For example, you have an AI play a 2D game, and it knows whether it's lost or won, and a point system, reward system, and there's different constants like was it greedy epsilon ratios, where it either goes down the path it already knows or chooses a random path, and anyway. It takes so long to learn all of this and truly memorize it long term. I just don't work with it every day. Classic reduced order modeling. Now these things I don't really know. Different ways to do surrogates. Yeah, physics informed ML pins is the only thing that I know a little bit of. Digital twins, digital shadow, one-way data. Bidirectional is digital twin, executable, controls prediction. Well, the executable one's the only one that's that cool. Yeah, you have agents do a lot of things. I don't know why that's in this. ChatGPT just threw that in there because it thought it was relevant to me, probably. Oh, this is trying to help me with business strategy. This is an issue I'm having. I really want to find a way to get into transhumanism, but it's not really a field yet. It's really just biology, and it's all siloed off and segregated, and people spend their entire careers in one little place. And that's why I wish I could come up with really good software to build for these labs so that I get exposure to all these different things and can build up an idea of what could be done, and then maybe do a spin-off company where I actually build an augmentation of some kind. I think the holy grail is like programmable biology, but every project I've ever looked up, that doesn't seem like they've gotten very far. Seems like an impossible problem. Okay, all the commercial tools. I think this is an optimization tool. That's the biggest one. ANSYS is really fancy. You can do all kinds of stuff, but they have that market. I'm not even gonna consider touching that. I think Fusion does optimization too. Siemens. I think a lot of these have digital twin spinouts. Well, Fluent is ANSYS, and Star, is that console? I don't know. This is another disadvantage I have, is that a lot of mechanical engineers and electrical engineers use these tools all the time, so they kind of know the ecosystem. They know what they need. But I am trying to go into biology, which is less mature, I think, from a simulation software standpoint. Here we go. Hey, look, telling me this is what I need to do. Yep, very interested in this. I don't think there is a lot of funding for this. I know Michael Levin's lab is working on it. Very interesting to me. Imagine you could regrow a hand. Imagine you could grow an organ. What else could you do? Regrow nerve cells or something? Cure paraplegics? Don't know. Very interesting. Reshape your body at will. Maybe there is a link between that and aging. You could turn back aging somehow. Don't know. Interesting though. Robotics. Okay, so I have a lot to learn, but I think I've got a good, very rough general overview of what's going on, more than I did 6 months ago. This is specific applications. It's crazy to me that each one of these spawns professionals that spend their whole life on them. I'm way too ADHD for this, I think. I like to hook all the things together. I think that's where I'm at. Understand them well enough to put Frankenstein together, you know? Yeah, this is funny. It's pinning me down. I've talked to ChatGPT too much. It knows a little bit too much about me. Alright. It thinks I should simulate a heart, but I don't know. I think that's going to be pretty hard. Could try it. Would be a fun thing to try. Alright. Where to go from here? See, a part of me wants to just contact these biomedical labs and try to get work, but you have to have a strong enough resume. And I have my simulator, I have all of my experience on here. It looks pretty good, but I don't know if it sells me. I don't know if they believe that I could actually build a visual system like this for biomedical. You know, they see a jet and they're like, oh, just aerodynamic CFD. It's tricky. I'm not sure. I would love to just sit here and code forever, but I've got to make money, you know. I've got contracts running out soon, so I've got to figure something out. Wrapping this one up.